challenges in parallel programming is how people try to maintain their code. It's very hard to maintain.
Yes.
So you provided 4 different levels of abstraction in the form of domain-specific languages that would facilitate the writing of programming languages, of parallel computation, if I understood well.
My focus is more on providing heterogeneous computing, but because we believe that one platform may not be enough to get the optimized time. So our focus is more on providing heterogeneous computing. What I mean by heterogeneous computing is you execute some in this. So yes, I haven't properly looked at how these tools help in the maintenance. That is one of the future studies we want to do, the human-based studies, to see that how these tools help in the, does it help in maintaining. There are other issues. I understand that if you generate code, there are still maintenance issues. Yes, we haven't looked at them.
And so as a follow-up, is there, you feel, so you have these 4 different levels of abstraction. The way you presented them, they seem discrete, but I feel that there is actually a continuum between them.
Yes.
So maybe can you elaborate on that?
Yes. I would say first, especially Mapper n-body solvers. I would say especially n-body solver is actually an extension of PP model, because it is actually coming above it. PP model, what we get from the PP model, we pass it to the n-body solver. The DSL we get from the PNP solver, we get that and pass it to PP model, and PP model process it. So there's a connection there that, even though I didn't show it, PNP solver, the n-body solver is actually sitting above the PP model. The things we are expecting people to write in PP model, I wrote as templates and they are reusing it. Is that what they are asking? Yeah. But there is no connection between Mapper view because they are specific I would say within the domain of HPC, there are clusters that are not connected well. That's what I think.
I have a question. So, when you're choosing an algorithm using for the PP model, how does the developer know which one will execute the best, with the best execution time? So how do they know which one to choose? Say, for example, there's 3 CUDA, MPI, OpenMP. They have the option of choosing one of those. How do they know which is the best choice?
Okay. Very handy solution is just execute and see.
Okay, so trial and error.
I'm serious because sometimes that is the best option. That's why they all need it. I have seen sometimes you just write an OpenMP, execute, see it. After that you write an MPI. But there's always sometimes, if it's an embarrassingly parallel program, it doesn't take a lot of memory. You can make the initial assumption, okay, this will be better in CUDA. But things like sorting, okay, the sorting is a reduction process. And you have MPI and OpenMP. If you have both 4-core machine available, I think it would be better to go with MPI because MPI reduction is better. Yes. Your experience, based on your experience about your sources, it's a hard question to answer.
Yeah. So basically, try all of them and then choose the best.
Wasn't that part of the phase 2 Air Force thing we were trying to do?
Yes. Okay, so that is a part of a phase 2 proposal.
Okay.
Yes, actually. So what it says that we can, even though we cannot get a clear-cut answer for it, we can make an intelligent guess based on the number of variables you use in your program, the number of memory you take, number of resources you have. You can make an intelligent guess. Okay, this should be good in this. for example, if that memory doesn't go in my GPU, I can't even think of executing my GPU. Right? If if he has enough memory, and if you're a lot of clusters, you can make an intelligent guess, but there is the final answer basically still say,
But the other way to look at that problem is, if you didn't have a tool to explore these options,
Yes.
what would the user do? The user would go for the easiest one, which is just OpenMP and say, I
Yeah.
don't want to invest my time
Yes.
in writing an API version because I just don't have the time to invest because it's a big learning. So
Okay.
go for the easiest one to do, even though you may get better performance in the project.
Right.
When you described Redo,
Mhm.
you mentioned your motivation being basically that Hadoop is rather unsafe and might fail at runtime frequently. Is Redo, is it just a process description language so that you can make sure that your real program follows this process, or does it actually write code in Redo?
Yeah, okay. The MapReduce is, you're right, MapReduce is a process description language. So the good thing about MapReduce, what about in Hadoop, if you're doing mapper or reducer, you have to, the output, has to match.
Yeah.
But in the MapReduce, what we have is we have only mapper. Mapper has only output. Reducer doesn't have input. Because the output of the mapper should be, when you specify both of them, you show compilation. That is redundancy, right? You don't have to specify both. You just specify mapper, output, or reducer input. That's how we do it. So we can do it in the compile time.
Yeah.
Yeah. We are not generating, as you're right, we are not generating the mapper function or reducer function. We just give them templates, then they can implement. That's what I mentioned by the two abstraction levels. The first two, we are only providing the infrastructure to interact and complete it. We are not generating entire code. But the last two, we are generating entire code. That's how we get go to higher level abstraction. We know domain more, we have more information, so we can help more.
So when you did the algorithm level, you focused on MapReduce. Is there something else that you have in mind for doing the algorithm level instead of just MapReduce? Something perhaps that fits a little bit more between the PPM model and the other levels?
Okay, yeah. The thing is that it is not, as I mentioned, it is not abstraction going up, like the map. It is not like that. So it is like different ways of looking at HPC problems. That's what I'm trying to do.
Would you please open up the beginning screen?
Can I go to the first slide?
Beginning slide. The very first slide. I'm taking it.
Hit 1 and enter.
Yeah.
All right. One. No.
Thank you.
All right. Well, we got to the side.
Yeah.
We'll do it later,
We don't know the result yet. That's how it's celebrated.
Correct. So in generating your programs from the model, I suppose that you had templates and so the parameters you would put in, you generate an execution code like GPU or CPU. Can you tell us a little bit about how you selected the particular templates, what kind of optimizations you did there, because you were showing us some data about the different performances in your experiments, but I was curious how you selected the specific configurations of those templates for those.
Okay, so I can answer this actually all abstraction models. So let's pick on N-body solver, right? So if you look at the answer in N-body solver level, we have a lot of information there because we know that this is going to be a problem. A typical example, 53.